talking about a couple of bits of work students of mine have done. And so the first piece with Kevin Clark and others is looking observationally at what kind of things BERT knows. So what are these attention heads looking at? And the interesting thing is that we find that once you're building these very rich high-parameter models and you're training them over very large amounts of text, the models actually act as little linguists, that they discover that, I'll be better at predicting words in context if I actually know about the structure of sentences. And if there are pronouns, it'd be kind of useful to know what those pronouns refer to, because that would help me predict what's likely to be happening next. And so effectively, what we're finding is that these very large, very rich language models, although they're only given this very, very simple objective function of predict the missing word that I've gapped out, that's doing well on that task is enough of an incentive that it's worth these models' while to say, it'd just be a good idea if I decoded all the structure, in my example, of English, but these models have also been applied to other languages. Because if I just sort of know about sentence structure, I'll just be able to do this task better. So what we have is, in a BERT model, we have many layers and we have many attention heads. And for each of those attention heads at each of those layers, we can look and see where it's paying attention for each position in the sentence. So there are the positions in the sentence. I love them both with sort of end of sentence symbols, and we could say for each of these positions, where is it attending? So for the word I, it's looking at the word love. For the word both, it's looking at the end of sentence and the word and so we can look at these patterns of attention and see what different attention heads do. What do we find out that they do? Well, there are a lot of different heads, and they do a lot of different things, but there are some interesting patterns. There are quite a lot of heads down the bottom of the model, which essentially just look everywhere. So effectively, these are heads that just get a broad idea of the context of what are all the other words in this sentence and sort of averages their word vectors. So in traditional NLP terms, we could call those bag of words heads because they're just sort of averaging the words that are around. There are some heads that basically just look at the previous or look at the next word. And well, that's certainly not a crazy thing to do, because we know from all of the work with traditional language models that the adjacent words are just the single best predictor if you're only going to look at one thing. So in particular, we find that at the very first layer of a BERT encoding, most of the heads, and the y-axis here is sort of showing the entropy over attention. So uniform attention would be maximum entropy. So the first layer, most of the heads are just sort of bag of word heads looking everywhere. And that kind of makes sense, because given that we're starting off this attention process just from a generic mask, you kind of can't have a strategy that's intelligent about knowing to look at your head word or look for the main verb or something like that. But as we go through the layers, especially in this middle section, that the heads become much more selective. And so what do those later level heads do? Well, if you look at them at first, it looks kind of confusing. So in the BERT model, there's sort of this technical point that there's these separator tokens that are being put between sentences. And if you look at these heads, what you find out is that in layers sort of 4 to 10 of the 12-layer model, most of the heads, most of the time, are looking at separator tokens or looking at periods or commas, and you sort of scratch your head because that makes no sense. And the answer to what's happening there is that that we seem to be having these selective feature extractors. So these are feature extractors that are active sometimes, just like a traditional symbolic machine learning feature extractor. And when they're not active, they just have this sort of no-op operation of staring at the separator token. And so the interesting question is, well, what do they do when they're actually active? And there are different answers for different heads, but quite a lot of them actually look at syntactic structure. So let me just sort of say a moment about syntactic structure here now. So as a linguist, when we think of a sentence's structure and meaning, we compose it via a syntax tree. So here's the sentence, the chef that ran to the store was out of food. And the crucial thing to notice is what's out of food. If you used anything like linear order, well, right next to was out of food in the sentence are the words the store. So you could naturally think the store was out of food, and so the store was the subject, which out of food is predicated of. But that's not the right meaning of this sentence. The right meaning of this sentence is it's the chef that was out of food, and that ran to the store is then this relative clause that's modifying the chef. And so this tree structure captures that, right? So the tree structure has that ran to the store is a dependent of modifies the chef, and it's the chef that is then the subject of was out of food. And so we use this kind of dependency representation which both marks which words depend on or modify other words, and commonly then we give these dependencies types for their grammatical relations. So the chef is the subject of the predicate was out of food, the is a determiner modifier of chef, and that ran is the head of the relative clause that modifies chef, etc. down the tree. And so what we can do is then say, well, let's look at these heads and see which word they attend to most, and see if what's attended to most corresponds to the arrows in my dependency tree on the previous slide, or strictly the arrows reversed, I think, as to do they attend to heads or do they attend to dependents. And what you find is a whole bunch of them actually pick out syntactic structures. So here's head 10 on the 8th layer of BERT, and basically it has direct objects attend back to their verbs. So it's the whole of a direct object NP actually. So what we have is Paine-Weber considered an even harder sell, and all of the words an even harder sell, the object, are depending back on considered. Or then it's recommending specific stocks, and we have specific stocks is attending back to recommended. So that's a direct object detector. And then over here, this next one, the 11th attention head at the same layer, is then a noun modifier structure pointer. So when you have in the huge new law, all of in the huge new are these noun modifiers modifying law, and it all looks across to them. Similarly, the fight, the is attending to fight. So we have a sort of a noun pre-modifier head pointer there. And so if we look at that, what we find is, it's not that there's one head that gives you the syntactic structure of the tree. You can't say head 7 on layer 10, that's syntax, just use it and you've got a great parser. But if you look over different heads, there are different ones that specialize in syntactic relations. And so for a whole bunch of syntactic relations that you conventionally have in linguistics, there are heads that pick them out with very high accuracy, like these numbers show. Somewhat even more surprising and funkily, there's actually a co-reference head. So head 4 on layer 5 gives you a semi-decent co-reference system. So here we have with Kim today as she got some expert opinions on the damage to her home. And so the word her is attending mostly to she, a bit to her. The word she is attending to her and Kim and she. And Kim is attending to Kim, right? It's pointing for co-reference. Joining peace talks between Israel and the Palestinians, the negotiation is attending back to talks and vice versa. So if you use this head, you don't actually have the world's best co-reference system. We can build better ones, but you actually sort of have a semi-decent baseline co-reference system, and it seems like it's picked out the value of that. So that's pretty cool. But to go further than that, you might want to sort of do some experiments on what's in BERT representations to try and see what is it capturing how in the way of syntax. And so for the last thing I'd like to present is sort of making a structural probe to look at the geometry of what BERT encodes for capturing syntax. And so what's the idea here? Well, starting off for BERT, all you have at different layers is you have these vectors corresponding to the original words. And it just seems that they're incommensurate with the kind of discrete syntactic tree structures that are hypothesized for human languages. But maybe we can make progress on that. And a way to make progress on that is to think about distances, because distance metrics can unify trees and vectors. So in this tree that we saw before, a way of saying that it's the chef that's out of food and not the store that's out of food is if we use the distance metric on trees, where we just count the number of edges in the tree between two words, well then the store is far away from what's out of food, whereas the chef is close to out of food. And well, we also want to know something about what's the head and what's a dependent of what to actually sort of understand depth in the parse tree. And so we could think of doing the same. If we have a rooted tree which has a root which is of depth 0 at the top, we can kind of count down from it to give depth in the tree. And well, that gives that parse depth we could think of as sort of like a norm, and we can also have norms in vector spaces and want to be capturing that as well. And so here's what we'd like to be able to do. So when we have BERT, at any layer of BERT, we've got a vector corresponding to each word. So we can put those into a vector space like this. And that's representations of the different words. Now, it's unreasonable to think that all of what's in this vector space is encoding syntax, because, well, actually most of what these neural models compute is meaning and context, and so syntax is only a small part of it. So we want to find a subspace in which we can capture syntax. And so the way we're going to do that is we're going to look for a linear transformation of the vectors that picks out the syntax part of what's going on. So we want to find a matrix B that we're going to multiply all the word vectors by, well, they're sort of the internal to BERT vectors by, to get out the syntax of the space. And then once we're in that subspace, what we'd like to do is have the property that the squared L2 distance approximates the tree distance. And I'll come back in a minute to why squared might be in there. And if we can do that, we'll say that there's an encoding of tree distance latent in our vector space. And with that property, we can recover the syntax tree for any sentence by just saying, well, give us the minimum spanning tree in this subspace, and that will be the syntactic structure for the sentence. And so our goal is to find that B. And so what we want to do is find a B, which is a single matrix that's used everywhere, right? That's the constraint, such that for all sentences, and we train it on sentences with human-given parsers, for all pairs of words in those sentences, we want a B that in the B transform subspace, that squared vector distance is very close to tree path distance. And then we can do the same with a different B for capturing depth in the parse tree. And if we do that, what do we find? We find that for sort of baselines of sort of simple non-contextual things, we can't find a very good subspace. But if we use these modern deep contextual embeddings, already with Elmo, which is the simplest one, we find a semi-decent subspace. And as we go to better models like BERT, we find better subspaces. So it's not perfect, but our subspaces do pretty much capture the structure of sentences. And we can see that. So here we're looking at distances between pairs of words, the tree distance on the right, and what BERT says the distance is on the left. And as you can see, they look pretty similar. And the same is then true for doing parse depth as well. And so that's kind of promising. And I just thought, yeah, let me just show this one. Right, so this then shows the parse depth. So the grey circles show the gold parse depth, which is always integral. Red is Elmo and blue is BERT. And you can see that BERT's modeling of parse depth is almost perfect, except over here where it goes a little bit off in the sentence. What you find out is that to make this probe B about 64 dimensions is enough, which maybe makes sense. That much of language is syntax, and all the rest of it is semantics, discourse, context, or something else. So the final thing I just wanted to mention is, well, why does it work best to use squared distance? At the time we did this work, we just found that was empirically true, and we're just sort of crude empirical people or something. But there was this kind of cool bit of work that came out of a group of people, Andy Conan, etc., from Google, who principally were interested in visualization, but they made a kind of interesting observation that might partially explain where square distance comes from. So mainly they were sort of wanting to use these representations to do clever visualizations of paths differences. But they noted the following thing, that there's an easy way to think of nodes and trees as having a natural vector embedding. So for each edge, you can assign an orthogonal unit embedding to it. And you could do that deliberately, or you could just rely on the fact that if you're in a high-dimensional space, random embeddings are almost orthogonal. And then so as you go down the tree, you can assign to each tree down the node the sum of the embeddings of the edges that point towards it. And so that gives you a representation of the nodes in a tree. And if you have such a representation, you can then work out the metric distances of edge paths in the tree that we've been using up until now by just subtracting these vectors, and you'll get the right answer. But then if you have these kind of encodings, they note the fact that you just can't embed tree distance of this form in a Euclidean space. It just doesn't work, because if you'd like to have nodes coming out of the node X, so all its children are 1 away, then all of those nodes should be 2 away from each other, but since you need to have 2 being less than 1 plus 1, you'd have to make all of the nodes collinear, that there's just no way to encode it in a Euclidean space. But on the other hand, if you go to a squared space, which they dub a Pythagorean embedding, well, then you can sort of use the corners of your hypercube to embed trees perfectly well. So it sort of makes sense that these squared distance should actually give you a better model. Well, you can think about that a bit more. But so the final thoughts that, and I should stop, is that this sort of unsupervised or really self-supervised predictor word and context learning has just been super duper successful for starting to build models that learn the structure of language. So really from sort of 1980 to 2015, the dominant thing that's been done in NLP people have been taking data sets and hand annotating linguistic structure on those data sets of various kinds. And it's starting to seem like, oh, maybe that was a large mistake and we shouldn't have ever been doing that, and we should have been just trying to work with self-supervision to learn the latent structure. And the really interesting thing, I think, as a linguist, is that from this very simple beginning of just predicting the next word, we actually seem to have built a device that's actually a language discovery device that is just for its own purposes saying, oh, I need to figure out the structure of human language. And that's actually just sort of an amazing thing that's happening. So although going big stretches computational resources and energy, and perhaps we're big enough now that we're bigger than human children get to see, it sort of seems like we've actually made huge progress in actually, for the first time, being able to build something that works as a language discovery device in an automated way.